So that gives us a reason for caring about chemical reactions. So in a chemical reaction, a chemical change is occurring. Existing substances are destroyed, new substances are formed. In that change, atoms are rearranged. They are separated from the molecules they were in, and their new molecules are created, but the atoms themselves are the same. It's taking Lego bricks, yeah, there we go again, Lego bricks, and building something new out of them. A combustion reaction is a specific type of reaction. Combustion is burning. What's necessary for something to burn? Oxygen. There has to be air, and the important component of the air is the oxygen. So a combustion reaction is something combining with oxygen, and in the process of that, it forms one or more oxygen-containing compounds. So when we burn fossil fuels, we're doing a combustion reaction, and the useful thing about combustion reactions is that they release energy, they release heat. So the heat produced in those combustion reactions is critical to supplying our society's energy needs. A chemical equation is a shorthand way of describing a chemical reaction. So the general pattern here is we list the reactants, the different chemicals that are reacting with each other. These are the things we're starting with. And then there's an arrow that shows the reactants are going to the products. And these are the things that are being produced. So the reactants react to produce the products, right? Equations give us a lot of information. They give us the formulas, the reactants and products. They often give us the states. Here are the abbreviations we use to indicate the physical state: G for gas, L for liquid, S for solid. AQ we see a lot, and that means it's aqueous, it's dissolved in water. So those are the states of the reactants and products. Not all chemical equations are going to have those, but many do. Another important thing that we get out of a chemical equation is the relative numbers of reactant and product molecules. Those relative numbers can be used to figure out the masses of reactants and products that are used and generated. So let's think about the combustion of methane. Methane is the primary gas found in natural gas, and methane burns in oxygen to produce carbon dioxide and water. So we can, this is methane, and we just scratched the surface. Actually, we didn't scratch the surface. We looked at the surface of organic nomenclature, and we learned that meth means one carbon, and this has all single bonds, so that's methane. Methane reacting with oxygen. This is O2 instead of O. Why do we write O2 here? Well, it is a gas, but other gases don't have a 2. It's one of the 7. There are 7 diatomic elements, right? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. If we ever have one of those as an element in an equation, it's Br2 or I2. Right? So oxygen is one of those, so it's O2. And we're producing carbon dioxide and water. Now, when I think of water, I think of a liquid, right? Why is this a gas? Because it's hot, right? So think about a natural gas flame. So maybe your gas stove at home or a Bunsen burner, and you're burning the natural gas. It's hot, right? What does water do at high temperatures? It evaporates, it turns into a gas. So this is a gas. So we can describe this reaction like this, but there's a problem here because at the end we have the same number of atoms of each element as we started with, and that's not what this equation is telling us. In this equation, we're starting with 2 oxygen atoms, and over here we have 2 oxygen atoms plus 1 oxygen atom, so now we have 3. Is that possible? Can we create oxygen atoms by burning something? No. All we can do is rearrange things. So that's a problem with this equation. There's also a problem with the hydrogens. Over here on the left, CH4, there's 4 hydrogen atoms. On the right side, we only have 2 hydrogen atoms. So again, it's not matching up. When we take the atoms apart and put them back together, we can't have leftover pieces, and we can't pull out new pieces from a box somewhere. We have to use all the pieces. So this equation is violating the law of conservation of mass, and natural laws cannot just be disobeyed. So we have to adjust our equation. We call this balancing the equation. So what we do is we put coefficients in front of the chemical formulas. So here I put a number 2 in front of O2, and this is saying that I have 2 of these molecules. And here we have nice pictures below, because if we can think of the pictures of the individual particles like Lego bricks, then the equation makes much more sense.
I thought you said we couldn't want to just add atoms to it.
Well, we cannot add atoms that were not present initially. The thing is that our equation was not telling us how much was present. Yeah, so it was our equation that was wrong. So here, CH4, so we could represent that here. The black is the carbon and the 4 whites are the hydrogens. And if I have 2 oxygen molecules, when I take these pieces apart, I can combine them and make these 3 things. And I'm using all of the balls that I started with, and I don't have any left over. I didn't need any extras. I fixed my equation by saying, well, I must need 2 oxygen molecules, and then in my products, I'm making 2 water molecules. So we are not, altering nature or twisting what actually happens. We are just adjusting our description of what's happening. Does anybody have any questions? So we should be able to count atoms in a chemical equation. So if we look at this one, it's asking how many oxygen atoms are on the right-hand side of the following equation. So right-hand side, we mean to the right of the arrow. That's like the balancing point here. So over on the right side, how many oxygen atoms are there? A bunch. Well, we could do the math in our heads, but then, so let's look at each of these individually. Here I have 2 molecules of Fe2O3. So I have 2 molecules, and each molecule has 3 oxygen atoms. So that's 6, right? And then in CO2, how many oxygen atoms are in one CO2 molecule? 2. And how many CO2 molecules do I have? 4. 4 times 2 is 8, right? So I have 6 plus 8, I have 14 oxygen atoms on the right side. Okay with that? I see a lot of students that get to this point in chemistry and they probably feel like they've muddled through somehow. But it just like, you're kind of making a guess and hoping it's right. It's really important to really understand what a chemical equation represents. And it isn't hard. It's very helpful if we think about pictures. If I talked about tricycles and bicycles and asked you how many wheels and said there were 2 tricycles and 4 bicycles, you'd be able to figure out how many wheels there were, right? Because you can see those things. Well, 2 tricycles, each tricycle has 3 wheels. There's 2 of them, so 6 wheels. 4 bicycles, bicycles have 2 wheels. 4 times 2 is 8. Add them together. It's exactly the same here, except it's hard to picture. And so that's why it's very helpful to be able to make pictures like this in your mind. A modeling kit can be helpful because you can actually make the molecules that you're starting with and take them apart and put them back together again and see, oh yeah, look at that, it's the same pieces. And once you get that clear in your head, then you don't need to draw pictures or play with models anymore because you can picture it in your head, right? Any questions? Okay, so we need to be able to balance chemical equations. So here's a guide. There are different ways to balance chemical equations, and what's ultimately important is you come up with the right answer. So this is a method called balancing by inspection. So you have to start out with a skeletal equation, the bare bones, right? You need the formulas for the reactants and the formulas for the products, and those formulas have to be correct. Then you're going to balance the atoms, and this is where things kind of go in different ways. I can give you a guideline of, start here, but I can't give you a set of rules that will work every single time and cause it to be quick and easy. So the recommendation here is to balance atoms that occur in more complex substances first, balance atoms and compounds before atoms and pure elements. You definitely want, well, actually that's not what I meant to. You always want to balance atoms that occur in free elements last. Because when you put a coefficient in front of a molecule, you change the number of all the atoms in the molecule, right? If I say there's 2 bicycles instead of 1, I've changed the number of wheels, but I've also changed, what does the 1 represent? Maybe the frames, right? A frame and 2 wheels makes a bicycle. So then I change the number of frames. So if I've already figured out and balanced the number of frames, and then I go mess up with the number of wheels, I change what I've already done. The great thing about leaving elements till the last is you can put a coefficient in front of them. They don't mess up anything else. Sometimes when you balance the equation, you might end up with coefficients that are fractions. We can't have fractions in our finished equation, so we need to clear those fractions. It's also possible to do it without getting into fractions, and then you should always check at the end to make sure that it's correct. So let's do some examples. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So this is a description of the chemical reaction in words. So we've got solid silicon dioxide, that's telling us the state and the name of the compound. We've learned nomenclature now, right? We're all just awesome at it. So we can figure out the formula. And is going to be the plus. So it's this thing plus solid carbon. To produce is the arrow, because those two things are making solid silicon carbide and plus carbon monoxide gas. So silicon dioxide. Well, what kind of an element is silicon? Is it a metal or a nonmetal? Well, technically it's a semi-metal or a metalloid, but what side of the line is it on? It's on the non-metal side, right? So it isn't written in the book, but my observation is that for the semi-metals, they are named as metals or non-metals depending on what side of the line they're on. So silicon is on the non-metal side, we're going to name it like a non-metal. So silicon dioxide, molecular compound, silicon and 2 oxygens, right? So SiO2, and I'm told that it's a solid. So I'm going to put S in parentheses after that. Plus solid carbon. I'm going to leave some space here in case I need a coefficient, so I don't have to make a mess. Solid carbon. What's the symbol for carbon? C. Is that a diatomic element? Horses need oats for clear brown eyes. The C is chlorine. It is not. Okay. Carbon is not a diatomic element, so we just write the C.
So the 7 starts at N?
Mm-hmm. The 7 starts at N, nitrogen, which is number 7. Isn't that cool? It starts at 7, makes a 7 for 7 elements. Of course, hydrogen has to mess things up. To produce silicon carbide. Hey Siri, what's the formula for silicon carbide?
The answer I found is CSI.
See, she changed her answers. It used to be so fun because she said, the answer I found is SIC. 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 If you do CSI, it's going to give you the same, you're going to balance it the same. And silicon carbide is not a compound that we're going to have you name or write formulas for very often. But silicon carbide, 2 nonmetals, right? And so we would normally use prefixes to tell how many. Neither of these has a prefix. So when we leave a prefix off, what's the number? It's 1. So SiC. Plus carbon monoxide gas. What's that? CO. Yes. Carbon and 1 oxygen. Okay, so that's practice from chapter 3. Now, to balance it. Do we see anything that's an element all by itself? The carbon is. So I want to leave that one for the end. A lot of times you can just start with the first element and work your way across, and it comes out just fine. If you start with one element and you're going along and you start to feel like you're in the woods going in circles because you just keep changing things and having to change things, stop and start in a different place. Also make sure that your formulas are correct, because if one of your formulas is wrong, it may be entirely impossible to balance the equation. So let's just look at silicon. How many silicons are on the left side of the arrow? 1. And how many are on the right side? 1. Well, great, that one's already fixed. How many oxygens are on the left side? 2. And how many on the right side? 1. So it's easier to add coefficients to make more rather than using fractions to make fewer. So if I've got 2 over here and I want 2 over here, I'm going to fix that by putting a coefficient of 2 in front of CO. I can't change the formula, but I can change how many molecules of that are in my equation. So now I've got 2 oxygens, and that didn't mess up the silicon. So the last one is carbon. So on this side I have 1 carbon. How many carbons on the right side? 3. Well, I can make this balance by putting a 3 here. Any questions? Let's do another one. Balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So one of our reactants is ethane, and they gave us the formula for that. That was kind of them, thank you. And it's a gas. We know that because they told us. What's the other reactant here? Gaseous oxygen. So it reacts, it combines with gaseous oxygen. So the symbol for oxygen, the elemental symbol is O. Is oxygen diatomic? Yes, it is. So I need to write O2 here. Because oxygen is like one of the junior high girls of the elements. Oxygen never goes out as individual atoms. Now, if it's with carbon, it's fine, but it's not going to be just an O by itself. So if we just have oxygen, it'll be two of them. They use the buddy system, and that's a gas. And then gaseous carbon dioxide, what's the formula for that? CO2. And gaseous water, H2O, gas. Okay? Now, this is good because it's a review of nomenclature, which we just learned, and we need some review of that. On an exam, typically, they'll give you the skeleton equation and ask you to balance it. Okay, so let's just start at the left and go across to the right. I'm also going to show you a method I think of as sort of a tally method. You may or may not find this to be helpful, but I'm going to show it to you in case you decide you want to try it. So I'm just going to draw a line down the middle where the arrow is, and then I'm going to sort of make a tally sheet of what elements I've got. So I've got carbon, I've got hydrogen, and I have oxygen. And then I'm going to look at each of the reactants and products and identify how many of each of those elements are in that. So in C2H6, how many carbons are there? 2. And how many hydrogens? And how many oxygens? In C2H6. There's 2 over here, but that's a separate thing. So in this, there's 0. Zeros tend to look like O's, and that gets confusing, so I'm just going to dash for nothing. Over here, how many carbons in this one? None. And how many hydrogens? None. How many oxygens? 2. You see what I'm doing? CO2, how many carbon atoms? 1. How many hydrogen atoms? None. How many oxygen atoms? 2. There's no carbon in water. There's 2 hydrogens and 1 oxygen. This is not always necessary, but if you get a complicated one, it can be helpful. So now I can look at the totals. I have 2 plus nothing, so I have 2 carbons there, and 1 plus nothing, 1 carbon here. Well, how do I make a 1 into a 2? I multiply by 2. So if I put a 2 in front of CO2, that's going to change all the atoms, right? So now I've got 2 atoms of carbon, and how many oxygen atoms? 4. So my carbon, 2 and 2, we're good. Let's look at hydrogens. So over here I've got 6 and nothing, so a total of 6, and over here I have a total of 2. What coefficient do I need in front of H2O? 3? Because if I have 3, then I have 3 times 2, 6 hydrogens, and 3 times 1, 3 oxygens. A little too early in the morning for me. When we did that, did we mess up the carbons at all? No? Okay, cool. So now we've got the carbon and the hydrogen balance, and we're going to come down here to oxygen and see what we can do. So on the left side I have 2 oxygens, and on the right side I have 4 plus 3 is 7. The oxygens are coming in pairs, but I want 7 of them, which is an odd number. If I multiply this by 3, I'll get 6, and if I multiply by 4, I'll get 8, right? One's too small, one's too big. I could use a fraction. I could multiply by 7/2, but yeah, you're shaking your head. No, we don't need to do fractions if we don't have to, right? I have a friend who teaches middle school math, and she says that fractions are the F word in math. At least for middle school students, they are. Well, what do we do? I call this the odd even. issue, right? One side's odd, the other side's even, and how do we make them the same? How do you make an odd number into an even number? Multiply by 2. Because if I multiply everything by 2, my 7 is going to turn into a 14, and then things are going to go much better, right? So I'm going to multiply everything by 2. So this was a 1, I'm going to make it a 2. Well, that changes everything down here. This is the thing I'm trying to figure out. I hadn't done anything there, so I'm just going to leave that blank. I'm going to multiply this by 2. And I'm going to multiply this by 2. So now 8 plus 6 is 14. Are my carbons and hydrogens still balanced? They are. So now I need a total of 14 oxygens, which is an even number. So here the oxygens are coming in pairs. I can figure out that I need 7 of them, right? 7 oxygens is going to give me a total of 14 oxygen atoms. Any questions? Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. So again, we start with the chemical equations. Lead-2 nitrate, is that an acid, a molecular compound, or an ionic compound? Ionic, right? Okay, so to write the formula for an ionic compound, I need the formulas for the ions with their charges. So I'm going to make some little notes to myself. I'm just going to write them above the name. So lead-2, lead is Pb, and what does the Roman numeral 2 tell me? It's the charge. So this is Pb 2+.
Do we always assume the transition metals are positive charge?
The transition metals will always be positive, yes, because metals only form positive ions. Always, always, always. Good question. Nitrate, NO3 minus. Why? Because I said so. It was in the list. You told us that it was what it was. Yeah, there's no other real reason. It's just because we decided to call it that, right? So NO3 minus. So I'm going to write the formula for lead-2 nitrate by looking at the formula for the ions with their charges. I'm going to put them together in a ratio that gives me a neutral compound, right? There's several different ways to accomplish that. If you're having troubles with that, please talk to me during lab. So that's going to give us PbNO3 2, because I need 2 of these to get a total of -2 charge to balance the +2 charge. And then I'm told it's aqueous, so I'm going to put AQ. And I realize that I'm going to run out of space, so I will just move that over. Okay, that and aqueous potassium chloride. What kind of an element is potassium? It's a metal. This is another ionic compound. So I need the elements, the ions with their charges. What charge does potassium take? +1. Why? It's in group 1. All the metals in group 1 make +1 ions. And then chlorine is Cl, and chloride has what charge? -1. Because we learned there's a pattern in the periodic table. If I start with argon, argon's a noble gas, doesn't make any ions. That one's 0, and I count backwards, I get -1. That's the charge for chlorine. So here I've got a positive and a negative charge. And so if I put one of each of those together, I'll get a neutral compound, KCl, and it says that that's aqueous. It's forming solid lead-2 chloride. Well, I already have all of the ion formulas here. What's happening, we'll talk about this later, they're just switching partners is what's happening. So I need to put lead-2 with chloride. So I consider the charges, and this is PbCl2, and I'm told that's a solid. I don't need a parentheses here because this is a single element. So I just have 2 chlorines. I needed the parentheses over here because this is a polyatomic ion, and I've got 2 of them. And I don't want to think I have 32 oxygens. And aqueous potassium nitrate. So potassium with nitrate is going to be KNO3. Any questions? So balancing this. I like to start at the beginning, just with the first element. It works out most of the time. So how many PBs do I have on the entire left side of this equation? 1. And how many do I have on the right side? 1. Cool, that one took care of itself. Now this NO3, I can balance the nitrogens and the oxygens separately, but the nitrate is still nitrate in the products. So this is like a unit of a Lego structure that we didn't take apart. We just took some stuff off of it and put different stuff on. But this NO3 was present in the beginning and is present in the end. I can treat it as a single thing. How many nitrate ions are in the reactants? 2. How many are in the products? 1. So I can make that into 2 by putting a 2 in front of KNO3. So I've got 1 lead on each side and 2 nitrates on each side. The next element I come to is potassium. So there's 1 potassium on the left side, and how many potassiums on the right side? There's 2. Because I fixed this so it's 2 KNO3s, so I've got 2 potassiums. So then I need to put a 2 here to make 2 potassiums over there. And that didn't mess up the nitrates or the leads, phew, right? And my last element is chlorine. So I have 2 chlorines here, and how many chlorines over here? 2. Cool. When we've got ionic compounds like this, a lot of times that last one will take care of itself. This is balancing chemical equations containing ionic compounds with polyatomic ions. We can take that polyatomic ion and balance it as a unit if it is also present in the products. Any questions?